A massive object is plunging toward the sun at a speed few things in the solar system ever reach. Within days, it will skim through the outer layers of the sun's atmosphere, entering an environment hot enough to tear apart rock, metal, and ice alike. From Earth, telescopes will watch as it brightens, distorts, and possibly breaks apart in real time. When an object passes this close to the sun, it is effectively forced open, its outer layers stripped away, its internal structure exposed under extreme heat and radiation. Could this object be connected to one of the most puzzling interstellar visitors ever observed? That earlier object, known as 3I Atlas, has already challenged expectations. Identified as an interstellar traveler passing through the solar system, it quickly stood out, not just because of its origin, but because of its inferred size and mass. Estimates suggest it is far larger than typical interstellar debris, with a mass on the order of 1 billion metric tons. This alone would make it noteworthy, but the real issue lies in probability. Based on current models, astronomers would expect to detect many smaller interstellar objects before encountering one of this scale. Yet observations have not followed that pattern. Instead, 3I Atlas appeared without the expected background population, raising the possibility that existing models of interstellar object distribution are incomplete. This discrepancy becomes clearer when compared to Oumuamua, the first known interstellar object detected passing through the solar system. Oumuamua was relatively small and faint, consistent with expectations that such objects should be far more common. If those expectations hold, then the discovery of a much larger object like 3I Atlas at this stage is statistically unlikely. Either smaller objects are being missed in large numbers, or the assumptions about how interstellar objects form and travel need to be revised. In either case, the presence of 3I Atlas introduces uncertainty into what was previously considered a developing but coherent field of study. As the object continued its path, it made a close approach to Jupiter, offering a potential opportunity for additional observation. Planetary flybys can sometimes reveal details about an object's trajectory or composition through gravitational interactions. However, in this case, the encounter did not provide significant new insight. The anomalies associated with 3I Atlas remained unresolved, and attention began to shift toward other ways of extracting information about such objects. One of the most effective methods involves observing objects under extreme conditions, specifically during close approaches to the sun. Sun-grazing trajectories expose objects to intense thermal and gravitational stress. As surface materials heat up, they begin to sublimate, releasing gas and dust. This process can reveal the composition of the outer layers, while structural weaknesses may lead to fragmentation, offering a glimpse into the interior. Because these events occur under natural conditions that cannot be replicated in laboratories, they provide a unique source of data. This is where the object designated C/2026A1, also known as MAPS, becomes particularly important. Discovered in early 2026, it is on a trajectory that will bring it extremely close to the sun. At its nearest point, it will pass within approximately 161,000 kilometers of the solar surface, well within the region known as the solar corona. During this passage, it is expected to reach speeds of around 557 kilometers per second, reflecting the strong gravitational influence of the sun. At first glance, MAPS might be classified as a member of the Kreutz family of sun-grazing comets, a group known for similar close solar approaches. However, several of its characteristics do not align with this classification. Its orbital period, estimated at nearly 1900 years, is significantly longer than that of typical Kreutz comets. Additionally, it was detected at a distance greater than 2 astronomical units from the sun, which is unusual for objects of this type. Such early detection suggests either a larger size or higher activity level than expected. Further complicating the picture is its brightness. Observations indicate that MAPS has been brightening more rapidly than predicted by standard models of comet behavior. This suggests that the processes driving its activity may differ from those observed in more typical comets. Possible explanations include variations in composition, such as a higher concentration of volatile materials, or structural properties that allow for more rapid release of gas and dust. However, none of these explanations fully account for the observed behavior, leaving room for further investigation. Given the unusual characteristics of both 3I Atlas and MAPS, it is natural to consider whether there might be a connection between them. The idea is straightforward if one object has already challenged expectations as a massive and poorly understood interstellar visitor, and another appears soon after with its own set of anomalies, it raises the possibility that they could share a common origin. One hypothesis is that MAPS could be a fragment of 3I Atlas, separated during an earlier disruption event and later captured into an orbit around the Sun. Such fragmentation is not unheard of in small bodies, as comets and asteroids can break apart due to thermal stress, rotational instability, or gravitational interactions. However, when this possibility is examined more closely, the evidence does not strongly support it. The orbital inclinations of the two objects differ by a substantial margin, indicating that they are moving along distinctly different planes, something that would be unlikely if they originated from the same parent body in the recent past. In addition, their estimated sizes complicate the picture further, as MAPS appears to be comparable in scale rather than a clearly smaller fragment, which is not typical of known breakup scenarios. Even so, the comparison highlights a broader issue within planetary science: the difficulty of classifying objects that do not conform to established categories. Scientific models rely on patterns derived from repeated observations, but both 3I Atlas and MAPS fall outside those patterns in important ways. 3I Atlas challenges expectations about the size distribution and frequency of interstellar objects, while MAPS raises questions about the behavior and classification of sun-grazing comets. When objects exhibit characteristics that blur these boundaries, it suggests that existing frameworks may not fully capture the diversity of bodies moving through and around the solar system. Rather than fitting neatly into predefined categories, these objects occupy a gray area that forces scientists to reconsider assumptions and refine their models. In this sense, anomalies are not just curiosities. They are signals that current understanding may be incomplete and that further investigation is needed. The upcoming solar encounter of MAPS provides a rare and valuable opportunity to address some of these uncertainties. As it passes through the solar corona, it will be exposed to extreme heat, radiation, and gravitational forces that can rapidly alter its physical state. Surface materials are expected to vaporize, releasing gas and dust that can be analyzed to determine composition, while internal stresses may lead to fragmentation that reveals its structure. Instruments on solar telescopes and space-based observatories will track changes in brightness, shape, and trajectory, offering real-time data on how the object responds to these conditions. If MAPS breaks apart, the resulting debris could provide additional clues, as different materials react differently to the intense solar environment. Regardless of whether it survives or disintegrates, the event will act as a natural experiment, yielding insights that can help scientists better understand not only MAPS itself, but also other unusual objects like 3I Atlas. The outcome of this encounter is uncertain. Some sun-grazing objects survive their close approach, while others disintegrate completely. Factors such as internal cohesion, rotation, and composition all play a role in determining the result. Regardless of the outcome, the data collected during this event will contribute to a better understanding of how such objects behave under extreme conditions. In a broader context, this information may help refine models of interstellar objects like 3I Atlas. By comparing observed behavior with theoretical predictions, scientists can identify gaps in current understanding and develop more accurate descriptions of these phenomena. This iterative process, observation, analysis, revision, is central to the advancement of science. At the same time, the discussion surrounding these objects highlights the role of interpretation in scientific work. When observations do not align with expectations, there is a tendency to favor explanations that fit within existing frameworks. While this approach can provide stability, it can also limit the exploration of alternative possibilities. The anomalies associated with 3I Atlas and MAPS serve as a reminder that unexpected data can be a valuable driver of progress. Public interest in these events reflects their broader significance. The idea of objects entering the solar system from interstellar space, or passing extremely close to the Sun, captures the imagination in a way that few other phenomena do. It connects abstract scientific concepts to observable events, making them more accessible and engaging. Ultimately, the question of whether part of 3I Atlas is heading toward the Sun remains unresolved. Current evidence suggests that MAPS is an independent object with its own unique characteristics. However, The coincidence of timing and the presence of anomalies in both cases ensure that the question will continue to be explored. As the date of the solar encounter approaches, attention will focus on what can be directly observed. The passage of maps near the Sun will provide a moment of clarity, an opportunity to gather data under conditions that reveal aspects of the object that would otherwise remain hidden. Whether this leads to definitive answers or raises new questions remains to be seen. What is certain is that events like this play a crucial role in expanding our understanding of the solar system and its surroundings. Each observation adds to a growing body of knowledge, helping to refine models and challenge assumptions. In this way, even a single object passing close to the Sun can have implications that extend far beyond its brief moment of visibility. For now, the focus remains on observation. An object is approaching the Sun, and with it comes the possibility of new insight. Whether it confirms existing theories or challenges them, the event will contribute to an ongoing effort to understand the complex and dynamic environment of our cosmic neighborhood.